everyone from the cloudy Copenhagen, and welcome to the training session Energy Efficiency eTraining to Mozambique, hosted by Copenhagen Center on Energy Efficiency. My name is Begonia. I'm working as a research assistant at the Copenhagen Center, and I will be the moderator for today's training session. A couple of things before we move to the main content of our training. This training session is going to be about 90 minutes long, including time for the Q&A at the end. In case you cannot stay until the end or want to get back to our presentations, all the materials and recording of the whole training session will be available in a few days on the Copenhagen Center's Knowledge Management System. And we have many other webinar and information there. Have a look. I will give you more information in a few minutes. Before we start discussing about today's training session, I would like to inform our attendees that we comply with the General Data Protection Act, also known as GDPR. This means that your personal data, such as name, email, workplace, is safely processed and stored, and all of your rights pursuant to the GDPR are respected. You have full access to the data being processed about you, and at any time you can request that the inaccurate data be deleted or rectified. For access or further information, please contact with the people that are presented here. A few things about the Copenhagen Center. The center conducts research and advisory activities in the field of energy efficiency and serves as energy efficiency hub for the Sustainable Energy for All initiative. The center has an established network of global, regional, and national partners with a broad range of stakeholders to help accelerate the implementation of energy efficiency activities. And now, I would like to briefly introduce to the speakers of today's training session. Mayur is the Sustainable Energy Team Leader of Cooper Alliance, the global network and managing director of the International Cooper Association in India. Currently, he's working with many developed and emerging economies in the Asia-Pacific and in the Middle East region in developing energy efficiency and renewable energy frameworks, policies, and market mechanisms. Soledad Garcia is an energy and industrial engineer. Currently, she is responsible for the technical support and project coordination of United for Efficiency, regional and country projects, like in Pakistan, for the development of their national energy efficiency policies, development of funding proposals, and implementation of regional harmonization of standards. Our other panelist is Rahul Raju. He's a senior expert on energy efficiency, and at UNEP-DTU Partnership, he focuses on the analysis of policy issues, conducts qualitative and quantitative studies, providing technical advice and other direct support associated with energy efficiency in countries and cities. Finally, I would like to inform that you can send us your questions during the presentations, and we will do our best to answer as many as we can at the end. Please do not forget to mention the name of the panelist that the question is for. And before I give the floor to the first panelist, I would like to briefly introduce you to a poll session with some questions just to have some insights on today's topic on heating, ventilation, and air conditioning. So as you can see, the first question is as follows. Do you work on operations, maintenance, or anything related to heating, ventilation, air conditioning systems? With two options, yes or no. I will give some seconds to reply to this question. Thank you. Okay, so we have received a 25% responses as yes and a 75% responses as no. Do you know how to evaluate heating, ventilation, and air conditioning components performances? Also with two options, yes or no. Okay, for this question, we have received a 38% responses as yes and a 63% responses as no. And finally, rate your technical know-how on heating, ventilation, air conditioning systems. Neil, moderate, or expert? For this question, we have received a 29% responses as Neil, 71% responses as moderate. Thank you so much for your participation. And now I would like to give the floor to our first panelist of the training session of today, Rahul Raju.
So good morning, everyone. Welcome back to the energy efficiency training. Earlier this week, we have covered module 2.2, where we learned about the main building envelope components, along with subsequent energy efficiency actions. We then covered module 2.3, where we have seen some key steps to conduct energy audits and adopt energy management for buildings. We have also covered 2.4 module, which presented some cost-effective solutions and information about energy efficiency lighting measures. So today I will be continuing with module 2, and I will be talking about energy efficiency in HVAC systems. The subject again is quite vast, and since I understand that there are participants from different professional backgrounds, I have divided this into two topics, two parts. That is, part one would be covering about basics of HVAC systems, that is types and terminologies. I think most of you, considering the polls, what we have just seen, most of you should be able to understand the basics, at least should be able to learn. I will then slightly get technical in the later part of the part one, where I will be slowly diving into the performance evaluation methods. Part two will be mostly covering the case studies as examples. So yes, I want every participant to understand the basic terminology. So I'm trying to do this in two different parts, so that they'll be relatable. Uh, there is quite a good content and lots of information that is available in the slides, which I'll be providing now. But I will be trying to tune the way the presentation is delivered, maybe to focus on simple basic aspects and encourage you all to connect later for the complex parts. So you will have the content accessible in the presentations once you receive them. However, I may not be covering all the information that is already present on the slides. I might be running through the slides and focus on or point you on a particular information or requirements wherever I feel it is necessary for you to understand. So we will be trying to follow a similar format here, answering these questions of what is HVAC system, why do we need it, and when do we need it, where do we need these systems in place, and question of how. So what is HVAC? Everyone is, most of us is aware of that it is nothing but heating, ventilation, and air conditioning system. Remember, it refers to a system, that is, it comprises of not just the heating and cooling equipment, but also the associated auxiliaries. That is, it could be circulating pumps and fans, blowers, cooling towers, air handling units, pipelines, insulations. If we go further detail into the system, you will have several other components that you may have to deal with depending on the type of the system you have in place. Some of the components you might come across are listed here. Each one of these components operations can actually impact the way your entire HVAC system performs. For example, if you consider air filters, as simple as air filters, if in case they are choked, then you could have some imbalances in the pressure, imbalances in the flow requirements. That could actually lead to inefficiencies in the system. Or if you probably consider, say, let's say, a cooling tower, if it is not giving the desired cooling water temperatures to your chillers, then it could lead to chiller inefficiencies in operations. So the question can be, why do we need HVAC systems, or why do we have to discuss or give importance to these systems in the first place? So when you look at a new construction and upcoming building, everyone is quite aware that the major expenditure goes to the envelope, that is the exterior walls, foundations, roof, windows, and doors. We have already seen some of the information on this regards earlier this week in module 2.2. Once the next investment part, that major key investments that will be going for into the building sector specifically is the HVAC after the envelope investments. So yes, this is one thing. Then if you look into the charts of here, the chart on the right actually shows you the percentage distribution of total number of proposals among different components and areas in a building. So please note, these you will be finding a lot of estimations and studies on these regards, but the one I am presenting is the practical ones, that is from energy efficiency and energy audit studies that I was associated with for the last 10 years. So these are quite, let's say, relevant and more practical numbers what I'm presenting now. So we see that the total number of energy conservation proposals that have come up from energy audit studies and energy efficiency studies for buildings, we see the highest share is for the HVAC systems. Then here, if you see in this chart, the details actually give you the share of energy savings for with respect to different components. The chart on the right again shows you the percentage share of each component to the total energy savings that were estimated and achieved. Once again, we see HVAC systems showing the largest chunk of energy savings from the entire building components. Again, here on the chart on the right, if you see, there are about 57% of the total energy cost savings achieved are again from HVAC systems. So it's basically these three charts actually gives you an idea that how important the HVAC systems are, and what, because of its potential, because of its number of proposals and cost savings that can be achieved. So when we look into what we see in our day-to-day activities is a mix and match of the above mentioned requirements here. You have exclusive heating, humidifying, and quality control under air conditioning. Then there are exclusive refrigeration, mostly used for industrial segment, food and process industries. And then there is a mix of mix of these two, that is, the cooling, dehumidifying operations, and air conditioning. Applications generally vary. If it is for comfort and space conditioning, that can be like, for example, office spaces, lobbies, conference halls in buildings, shop floors, and industries. That's for comfort conditioning. Then the systems can be used for process cooling, that is mostly for industrial applications, let's say maintaining bearing temperatures of a machine or an equipment, trying to maintain reactor conditions or heat exchanger temperatures and all. Brine systems again are generally used for critical applications where instead of water they use brine solutions for circulation. You can mostly see this often in pharmaceutical industries and all. So the question of how, we will be dealing with three different questions actually: how the HVAC system works, how we would assess the energy efficiency performance, and how to save energy. The first part here. So under the cooling and air conditioning requirements, basically you will have three types of systems here: vapor compression system, vapor absorption system, and evaporative cooling system. Let's go to the first part. If you see, have a simple fundamentals that will be required. If you see, you must have come across your probably at your homes or your offices, you will be having this simple split ACs, right? There's an indoor unit and then there is an outdoor unit. For the indoor unit, you generally there is a loop wherein the indoor air gets exchanges heat, gets cooled with the refrigerant at the evaporator. Then at the outdoor unit is the refrigerant which exchanges heat with the outdoor air, that is, it releases its heat, gets cooled, and gets back. So that's how the simple fundamental works here in vapor compression systems. So you have many other similar type of, you must have come across these different types of air conditioning systems that you might be aware of: the window air conditioning, package type, or split type. And for slightly bigger capacities, for mostly for office users and all, mid-level office users and all, you will have these type of systems that are used. Now, there are of course larger systems. The fundamental components again remains the same. These are actually for air-cooled systems. So in order to, as I've said, the fundamental components actually remains the same. In order to cater to larger areas, there would be no direct contact of air to the evaporator. Instead, you would be using water. The water gets cooled and this chilled water is circulated to the user ends to be used as the at air handling units or FCUs and all. On the condenser side, heat exchange is still done with air. only that you have large banks of fans instead of smaller ones. So, like unlike your conventional or traditional residential or smaller capacity air conditioning units, have larger banks of fans here, wherein reject that heat from the refrigerant. So these type of air cooled systems are usually used for areas where there is water scarcity or strict water regulations. If this is not the problem, if the water is not the problem, then people can go for the higher capacity water cooled systems. Again, the fundamental components remains the same. That is the evaporator and the condenser. The medium of heat exchange only changes here. That is, here even the condenser side, you have heat exchange being done with water, and then you will have another additional component called cooling towers in place. So there is a thermodynamic graph here. I will not be explaining that, but it's for your reference later when you have the slides. But in short, I'll explain the process here with this diagram. Basically, fundamentals here: the evaporator, wherein refrigerant absorbs heat from the medium, that could be air or water. That means the air or water gets cooled. And then you have a condenser here, where the refrigerant rejects the heat to a medium, that again can be air or water. And then you have the compressor and the expansion valves, which actually enable the refrigerant to do what it is meant to do, that is absorbing and ejecting heat. The terms of you have the different types of vapor compression systems, mostly reciprocating or centrifugal type or screw type. Depending on the type and usage, you will be using any of these type of systems for your requirements. Then, and of course, the type and usage, that means based on your capacities that you need, or based on the temperatures that you are dealing with. So that way you will be having these kind of equipments. Any of these types you will be using. And of course, there is also vapor absorption systems. The operational process is slightly complex. I will not get into the details, but I do have slides explaining the process in case someone is interested. The slides will be shared to you all. So if you still have queries, you can reach out to me on email. What we need to note here for now is that instead of a conventional refrigerant, you have two other components here. That is water, which acts as a refrigerant, and then there is lithium bromide solution, which acts as an absorbent. This slide gives you the different types of vapor absorption machines, that VAM, that is available based on your requirement, based on the heat source that is available, based on the quality of heat that is available. Why did I actually introduce VAM here for y'all is you can see its advantages and disadvantages here, the comparison between two types of systems that are available under the refrigeration and air conditioning systems. So if you look into the energy input, the conventional vapor compression machines, that it can be something as simple as your air conditioning units in your homes or offices, or to the larger systems of air cooled and water cooled chiller systems. They mostly rely on electricity for operating the compressor motor. The VAM machines, on the other hand, the primary input of energy is heat. Electricity is required, but it's in very small amounts to operate those circulating pumps within the equipment. So this way, you do not have to consume a lot of electricity here, but you might be needing another form of energy, that is heat energy. With respect to the efficiencies, the vapor compression machines are quite efficient with a COP of anywhere about 4 to 5. The VAM machines are again slightly inefficient. The heat rejection factors are for VAM machines are on the higher side. That means to reject that heat that is being absorbed, you will be requiring a lot of higher capacity cooling tower or pump circulation capacities. So, but in short, I would personally recommend, or generally it is recommended by most of them, that if you use VAM, you have to use it only when you have some source of waste heat or cheaper fuel source, or else it is generally not recommended. The third part is the evaporative cooling, where air is brought into close contact with the water to cool it to a temperature close to wet bulb temperature. Mostly shop floors and other comfortable climate zones, no? There people use this kind of mostly the dry climatic zones where places like dry regions where they can use this type of systems where you don't have any refrigerant or something that is or compressors being involved here. It's just heat exchange from water and air. Moving to the heating part, I will share different types of heating systems that can be used for HVAC systems. Usually the most common and applicable ones, possibly for Mozambique region, would be solar thermal boilers, heat pumps. I'm not discussing the geothermal source now. So active solar heating systems use solar energy to heat a fluid. It could be either liquid or air, and then transfer the solar heat directly to your interior spaces or to a storage system for later use. And these are different types of boilers. You will have you might be using boilers for generating steam or hot water generation for various purposes. It could be for your washrooms or kitchen or dehumidifiers. It can so boilers can be either gas fired boilers or electrical boilers or fuel, that is oil or diesel based boilers. Earlier I did discuss about this integration part, that is like here in this case you have solar thermal integrated with the conventional boiler to give you the necessary the heat or hot water and steam requirements. Then, of course, you do have heat pumps. Heat pumps also operate on the principle of vapor compression cooling, similar to what we have seen in cooling and air conditioning segment earlier. For climates with moderate heating and cooling needs, heat pumps offer, as an energy efficient alternative to furnaces and all. Like your refrigerator and other air conditioning cooling units, heat pumps also use electricity. But the fundamental here is you have the heat pumps cools the area cools the area more cooler, and then it makes the warm space even more warmer. That means it's literally quite opposite the air conditioning or refrigeration units where they use electricity to move heat from a warm space to a cool space. So the operation is simple. It's just that example here, if in case this is the place that is cooling, it should be your internal your indoor air unit, if it would be for your air conditioning unit. But if it is for heat pump, this would be an outdoor unit wherein the heat is being rejected here. And then you have these electrical resistance heaters, mostly portable ones and all, which are conventional. To the ventilation types, the major part of components are fans and blowers. This slide actually gives you different types of fans and blowers that may be used for various applications depending on the flows and pressures that one is working with. Of course, the radial part, radial blade is not a common one, but the remaining types are often the most commonly used types for HVAC systems. You can see here, based on the flow and pressure requirements, the applications vary for different fan types. Moving to the pumps, there are again a lot of classification of pumps, but mostly for HVAC systems, more often they use centrifugal type of pumps. Cooling towers, again there are different types of cooling towers for different purposes. Again, for HVAC systems, we have come across mostly the induced draft counterflow tower with fills, or induced draft double flow with cross tower fills. Basically, you have water being sprinkled from the top over a fill, and then you have air being sucked from the bottom. There's heat exchange, that is counterflow that happens, and then the air is vented out. The water, that is cold water, is taken for your user areas or for the chillers. So how we assess the efficiency performances? I'm sure most of you by now are aware of energy efficiency labeling and ratings. We talked about this in our earlier presentations also, and it is quite available we may also be getting to know more about it, about the residential and the household sector energy efficiency measures in the following presentations also after me. So I took this opportunity to introduce you all to the content that is either less available, or even if it is available, they are mostly scattered. The scope also will be mostly covering for large building setup, like commercial buildings, office parks, hotels, which usually prefer to have a centralized system in these places. So before moving on, the basic terminology which everyone should be aware of when it comes to HVAC system is the cooling effect of it. That is the terminologies that they usually use for day-to-day activities. Here we talk about TR, that is tons of refrigeration. It is defined as the quantity of heat that needs to be removed uh, in order to form 1 ton of ice in 24 hours when the initial temperature of the water is zero. In simpler terms, 1 tons of refrigeration is equivalent to about 3024 kilocalorie per hour heat content wise. It is also equivalent to 3.51 kilowatt or 12,000 BTU per hour. You must have come across different energy efficiency ratios on different nameplates of the HVAC systems. So to avoid any confusion, you can always look into this slide for conversions, because different suppliers represent the ratios in different formats. So you can to compare on a similar level, you can use these conversion factors and definitions to compare two different companies or two different air conditioning units, the efficiencies. So for a large building setup, generally they have these big large chillers in place. So when you're evaluating the chiller performance, then you will be needing to either measure or take these parameters into account. If it is an auditing team that comes, they would be measuring these parameters. But also lately, most of the buildings are coming up with their own building management systems where they capture all these parameters into a single control system and they keep monitoring. And this is a formula for your reference. You can use this based on the parameters that you have measured. You can substitute them and actually find out what is the cooling load that is being developed by the chiller. I have also given you an example here. Later, you can refer whenever it's possible for you. It basically gives you how to evaluate an example for the cooling load, and then also how to evaluate the specific consumption here. As a thumb rule, the lower the specific power consumption, the more efficient. So you can compare this operating values with your design rated values and see what is the deviation and all. And also, I have given you in the previous slides how to convert it into, let's say, COP or energy efficiency ratio and all. So that can also be converted and compared. In case there are some thumb rules you will be finding, standards you'll be finding all over the place. So mostly, like for example, this one. It's basically to have a rough idea about how much cooling load I'll be requiring, or what is the capacity of air conditioning system that I have to install for a given area that is available for me. It could be office space, office cabins, or a medium size office or something like that. But please note that these are generally for an idea, an indicative purpose. You should not be taking these as a basis for investment grade activities. For that, you need to have a proper study done to evaluate what are the different heating loads. It could be your internal loads or your solar heat loads. Everything have to be taken into consideration, and you should not go based on the conversion factors here. For the pumps, generally you will be needing some three important parameters that have to be measured, or you will be having these displayed into your BMS systems if you have one, where monitoring control systems. So it's basically the water flow, the pump head that is developed, and the power consumption. And this slide gives you how to evaluate the pump efficiencies. You can always evaluate the pump efficiencies and then compare it with the design details, and then you can always see if there is any deviation, why it is deviating, and further investigation can be done. I'm giving you an example with numbers, how to evaluate pump efficiencies. So I need your attention here because yes, if you are able to measure the parameters or you have the parameters in place and evaluate the performances, that is great. But if you do not have these resources, then this is something you can look into. You can ask your suppliers, pump suppliers, to you can actually demand them to give you the pump curve they should be having, that they are actually they are supposed to give you the pump curve. So through the pump curves, actually you can identify and approximately what is your current level of operations and efficiencies and all. I'll just give you an example here. So let's say I can measure the head based with respect to the my on-site pressure gauges, both on the suction and the discharge side. I will measure the head. Then if I draw a line like this, then I can actually find out what is the efficiency of the pump that is operating. Here now it is 73%. Then if I further extend the line, then I'll be knowing what flow my pump is operating at. And then also this gives me the power, what is the power consumption. So it is mix and match. So if you have any of the parameters, you can find the other parameters using the pump curves. So yes, it is important that if you do not have those resources of measuring and doing all the activities, you can either, the simplest form is to at least demand for this pump curve. Fans and blowers, this is slightly complex, but yes, basically you'll be needing an instrument called manometer. It can be either portable or it can be already installed if you have BMS system in place and you are capturing all these data. So basically you'll be measuring the pressure in the ducts, both on the return side and the supply side. And this is again for your later reference. I have given a step-by-step process for how to evaluate your efficiencies of the fans and blowers. So same like the pump curves, you can also demand for fan curves. The fans will also have similar curve, similar patterns. If you have one or two parameters, you can actually accordingly find out the other values, the efficiencies or the pressures and operating pressures and all, or even the flows. Moving to the cooling tower performance testing, these are the different parameters that I'll be needing to actually evaluate the performance of the cooling tower. And these are the different formulas. So basically I'll be trying to measure what is the range, what is the approach, what is the effectiveness. So these three indicators, I would say, can give you actual indication about how your cooling tower is performing. You can also evaluate what is what up to what extent there you have what you are losing water in terms of evaporation through cooling tower. HUs, if you have mostly centralized units, centralized air conditioning systems, then air handling units will be in place. So these are the different parameters that you will be required to measure or monitor for evaluating the performances of the air handling units. I've also shared you some sample calculation on how to evaluate the performances of air handling units. The similar concept can also be applied in a crude way for package units or your direct exchange units. That is your smaller capacity units, which I've shown in the earlier slide, in initial slides. This can also be done with respect to the outdoor measuring at the outdoor units. There are different complex methods also that will be measured. Mostly the companies, professional companies would come and do those measurements, but they are quite complex for now. And then you have heat pump performance. Basically, it is also measured in terms of COP. I mean, you get the indicators are given in terms of COP, the efficiencies. That is, if you say heat pump COP is 4, that means the heat pump releases about 4 kilowatt of heat, that useful heat for you, by consuming about 1 kilowatt equivalent of electric power. Then you do have boiler systems in place. The output here, of course, what I've indicated is for the steam generation, but you can also use consider hot water, the similar concept here, that is heat output by heat input. This is mostly a direct method which I'm showing now for calculation. There is another indirect method which gives you more accurate results, but a bit more complex to explain right now because it needs more of a stoichiometric analysis and oxygen measurements and all these things. If someone's interested in that, please write to me. I will direct you to the right sources for that evaluation also. So we were moving to how to save energy. Yes, coming to the air conditioning and refrigeration parts, we have seen most of the energy efficiency measures linked to building envelope during module 1.2. So we will be looking at the most common possible energy efficiency measures in other active systems. Uh, the first and the foremost, yes, we need to follow what are the different, try to have the best energy labeling standards available. Uh, Lately, we are getting some inverter grade integrated products also for air conditioning units. The normal split ACs and all, they do come with inverter options also, which actually consumes much less power compared to the conventional ones. Then yes, if for larger systems, generally the heat exchange happens over the heat exchanging surfaces, so they have to be maintained. That is the evaporator, condenser coils, and cooling coils and all. Matching capacity to system load. More often, we see that people tend to design or over design than the required ones. So that again leads you to inefficiencies due to partial operations and all. So yes, you need to make sure that yes, you have to see that your system capacities and cooling loads match. Capacity control, yes, I've talked about. Basically, this is about when there is you cannot actually have constant low cooling loads or heating loads throughout the year, right? There's always some variation. So according, if the variation is way too high, then it is important that you have capacity controls in place. These are again some common measures where then you need to check the insulation health and all, because mostly I've seen this is the most neglected part. These brown color pipes, what you see, you might be seeing everywhere, lying open and bare. These needs to be insulated for efficient operations. You can also use, let's say, VAV systems or heat recovery options for enhancing your efficiencies or improving your energy content. So I was talking about the control systems based on the for the chiller units, based on the type of chiller conditioning system that is there. You have different type of capacity controls. And, again, not one solution does not work for everything, so they have their own individual capacity and different types of capacity controls. This is the slide I want to again get your attention. This is something very you can use it as a thumb rule. I would say you can apply for your day-to-day quick assessments wherever applicable. So in general, the design would be the flow requirements for chilled water, condenser water. This would be the design requirements. That is about 0.68 meter cube per hour for every TR water is required. And then again, generally you must be coming across certain slogans or drives that they say, increase your set point temperature by certain degrees and do not maintain low set point temperatures, like not to maintain 18 degrees. Why not go to 21 degrees or 22 degrees as your air conditioning set temperatures and all, because this is the reason. So every 1 degree raise in your evaporator side or your set temperatures, you can actually save almost equivalent of 3% on the power consumption. So that way. Then of course, zoning. This is quite important. Often I see large office spaces with or about 50 to 100 people sitting in a big large hall, and only one or two working in that. For that, entire office space has to be conditioned, and the air conditioning systems have to be switched on. So instead of that, if you have the zoning systems in place, like instead of one zone you have multiple zones, then you can actually you can actually cater to individual zone needs. That way you will not be requiring to use larger systems. You can always optimize your consumption levels. For fans, pumps, and blowers, generally the most important thing, what most starking thing that I would see is oversizing, because one of the common mistakes everyone tends to make. Uh, Basically, you can identify if your system is oversized by checking if your, let's say, the control valves are highly throttled, or you have excessive noise that is coming up, or there are regular maintenance issues, uh, or there are any heavy bypassing is happening for the water or air that is included. Of course, this can be, the oversizing is done either due to, let's say, having safety margins, or having some larger proposals in the future, which that future never barely comes or rarely comes. Uh, Something like that, or you might be getting something in a cheap deal, so people tend to purchase a larger equipment though they do not require it. So that way you will be losing a lot of energy, though you get a good deal in your initial investment. Yes. So you can also use control systems like variable speed drives and variable fluid coupling based on your capacity regulation requirements. So talking about control systems, is a damper for fans, especially. You have a damper control that is can be either included, but can be actually there at the suction side or the delivery side. Damper is generally the, simpler control system, where but actually it causes a lot of energy loss. The inlet guide vanes, actually, this is usually for larger volumes that when they are handled, the fans. So this reduces your shock losses due to flow deflection, and hence, less energy loss is happening here. So here different types of fans and blowers are there, and their approximate peak efficiency ranges for your reference. For heating again, see, generally people do tend to use electrical resistance heating, mostly for homes and all. But yes, uh, it does convert 100% of all the electrical energy that is used into heat energy. So it might look efficient for you, but if you look into the bigger picture in terms of sustainability, if you remember one of the initial presentations I have shown you, how there is energy loss that is happens from the generation side till the user. So barely you are getting hardly 50% of energy that is actually being used, generated. So that way it is one of the most inefficient ones. So I would avoid using electrical resistance heaters. But if you do not have any other options, but you have only electricity as a choice, then if your climate or the weather conditions favor, then you can opt for heat pumps rather, which should actually cut down almost your electricity use by 50%. Then yes, insulation and pipelines of the equipment are required. If you have thermostatic regulators can also be used if you have radiators in place. For building level, boilers may not be comprising of a very complicated system as compared to industrial boilers. Most of the time, it is more or less a plug and play option also are available. So in short, you need to be looking for, if in case you have a fuel fired boilers in place, mostly applicable for hotels and large complexes and all, where heating solutions are provided. The optimal stack temperatures need to be looked into. The temperature, because these are the different forms of where losses can happen. If you have higher stack temperatures, that means you are losing a lot of heat there. So these are the different conditions which you can look into to avoid excess losses and improve your efficiencies. So yes, for residential and commercial buildings, there are three classifications: low efficiency boilers, and mid efficiency boilers, and high efficiency boilers. Based on that classification, you have different the information here, wherein you can basically for mid efficiency and all, you will be using an additional blowers or fans that to control the combustion air and gases. For higher efficiency, it also uses an additional heat exchanger where it condenses the flue gases and takes up the extra heat before losing it to the atmosphere. So yes, this is part one. So we will continue with part two now. Here I will be discussing some case studies. I may not go into deep technical details for two reasons though. The content is based on real projects that have been actually implemented and realized energy savings. So there is certain level of, let's say, confidentiality also comes into picture. So not all data will be revealed here. The content is intended to reach out for every participant, considering that not everyone is uh, aware of HVAC systems or working on day-to-day basis in HVAC systems. So an overview of what a problem is, what the final solution was implemented, and what are the resultant energy savings that were achieved will be presented. This should actually give you a direction and confidence in what measures actually work, what exactly is happening in the HVAC side in terms of energy efficiency measures. Of course, I will be giving you hardly 10 case studies, but not everything. But there will be number of uh, measures that can be incorporated depending on the type and the conditions or the operational conditions that are going on in the system. So case one, it's about adopting VRF systems or variable refrigerant flow systems. A VRF system typically consists of an outdoor unit with multiple compressors and different types of indoor units for different zones. It also comes with a highly sophisticated, electronic controls center, which it can enable zone-wise climate controls. So here, this was for an office building actually, wherein they had about 10 direct exchange duct type individual air conditioning units, a total capacity of 55.5 TR. And they were actually very old, deteriorated, and not much maintained well. So we have actually, instead of replacing them with similar type of air conditioning units, we have recommended them to go for a VRF system in place, so that to cater to all the 10 zones that they wanted to condition. That way, once after installation, they have measured and they have seen that they were achieving about 59,000 units per year energy savings. And this is an office building, so this savings is only for about 10 hours of daily operations on weekdays. Case two, it's about having variable frequency drive for chiller operations. This is not, though the technology is available, not many still use it for chillers. Yes, variable frequency drives are used for different other applications, but for specifically for chillers, it's very rarely, not quite often you come across, because people are either not aware of, or yeah. So this have to be looked into. So this actually gives you one of the facilities actually. So the design chiller that was the design details of the chiller that was present, 250 TR chiller, that is two chillers they have. So chiller one was with VFD and chiller two was without VFD. Both were operating for same conditions. If you look here, chiller with VFD, the orange one has this is for a 24-hour duration captured data. The energy consumption every hour for chiller one with VFD is low compared to that of the chiller two, though both are subjected to same cooling loads and operational conditions. Why? Because the chiller with VFD actually has the flexibility to modulate its power consumption as per the cooling load demand, and hence during low cooling loads, it would consume less power than compared to the chiller without VFD. Further technical details here, if you look into the efficiencies point of view, the chiller one with VFD, this is a red curve. If you see, specific power consumption is low, that is, it is relatively efficient compared to the chiller 2 specific power consumption here. So the difference is like compared, the energy consumption difference is about 2.2 lakh units on an annual basis. That is, the chiller one with VFD consumes 2.2 lakh units less energy compared to the one without VFD. Optimizing of cooling tower operations. So basically, there was a building complex which had water-cooled chillers and for their air conditioning needs, and then they have this cooling towers to reject the heat from the chillers. So we have seen the role of cooling towers in the HVAC systems. So the cooling tower fans were operating with full speed, irrespective of the ambient conditions. Now, the job of the cooling tower is to take the cooling water, the hot water that comes from the chillers or the other process areas. It rejects that heat into the atmosphere, cools down the water, and then it sends back to the user end requirements. So the set point was actually fixed at 24 degrees. That means if the cooling water temperature from the cooling tower reduces to 24 degrees, then the cooling tower fans would turn off. And then when the temperature increases, the fans would turn on again. So the intention, the approach was, the intention was good, but the fundamental approach was a flaw there, because as per the ambient atmospheric conditions, if you see, the wet bulb temperature is itself about 25 to 26 degrees centigrade. That is, it is highly, so it would be highly impossible for the cooling water to reach 24 degrees in the first place. You should know that through the concept of this evaporative cooling, the water temperature cannot go less than the wet bulb temperature. So we have recommended to change the set points regularly with respect to the ambient wet bulb temperatures, and also install a variable frequency drive for the cooling tower fan motors, with of course with respect to cooling water leaving temperature feedback. So this way it is not an on and off operation, but the drive actually regulates the frequencies and operates its power consumption as per the water temperature requirements. So for example, if my set point is, let's say, 26 degrees and my cooling water temperature is now 28 degrees, then the fan drive would be operating at full speed to help me achieve that 26 degrees centigrade. If my cooling water temperature is, let's say, 26.5 degrees, then which is closer to my set point of 26 degrees, then my fan drive would probably operating at about somewhere about 65 to 70 or 80% of the full speed capacity. So this way I would be consuming less power. So through this recommendation can also be advantageous for accounting to seasonal or daily weather changes in atmospheric conditions. At times days can be hotter and nights can be colder. So this way they were able to achieve about 0.43 lakh units per year with a simple payback of less than a year. So this is case 4, wherein it is about rectifying your system flows and pressures. So this particular facility had about 2 chillers of 1000 TR capacities, both running in parallel operations. The facility had state-of-art technologies with everything installed. There's variable frequency drives, there is control systems in place, there's monitoring systems in place. Everything was quite perfect in terms of installations. But the only problem was you cannot rely completely on the control systems. Machines can do only work to a certain extent. Ultimately, it is us, the humans, who you have to do the job, right? So to apply logics, because what happened is there were certain places where the control system was showing that the walls were open, but in reality, when we were measuring the flows and all, we found out that there was some throttling happening, there were pressure imbalances and all. So we had to, through the measurements, physical measurements, we had to tune the systems, the control systems first, and then ensure that there is sufficient water that is going for the catered to the chillers and other air conditioning systems to improve the overall operational efficiency. So if you look into the graph here, this is a control system graph, the monitoring system in place. So this is a system monitored information. This is not plotted by us. So if you see, there were 2 chillers, chiller number 4 and chiller number 6. They were initially consuming about 96 kilowatt and 243 kilowatt. After intervening with different measures to improvise the operational efficiency of the entire system, the power consumption has come down to 237 kilowatt and 214 kilowatt. To look into the COP or specific power consumption values also before and after, the system has improvised. So on an annual basis, they were able to achieve about 6.3 lakh units. And this is basically no investments have gone into this. It's just about trying to rectify improve your operational efficiencies and not completely rely on your control systems, but also have some logic in place to identify where there are any flaws or not. Case 5, it's about, this is actually not specific to buildings, but it is more of an industrial setup. But I would quickly like to show how the VAM machines, vapor absorption machines, can help you save energy. So This facility had about 2,000 TR chillers in place, and then also two 545 TR VAM machines in place. See, what happened was the facility was actually giving priority to the centrifugal chillers first, and then if the cooling load is still required, there is a demand, then they would go as a backup for the VAM machines. But during the study, we have seen that they have enough good amount of heat that was available that was being wasted, and the heat source was easily at around 160 to 180 degrees centigrade. So it was a simple switch in process wherein we have asked them to operate or give primary preference to the VAM machines to cater to the cooling loads. And if you still require some more cooling load to be catered to, then you can call in or touch in the centrifugal chillers operational practices. So that way, we have seen that almost energy savings of almost close to 14.4 lakh units were being saved based on, because you were actually utilizing the existing heat source without going it waste, and then you are also saving on the electrical energy consumption that you would have used if you used full-time centrifugal chillers. For case 6, I will show you why not to use VAM. So basically, this was in one of the hospital setup. They had this 500 TR VAM machines, which used to consume biodiesel, almost 160 to 170 liters per hour. So that's quite a lot of fuel. Of course, they had their reasons when they were actually setting up the facility. Uh, they had this intention to go green, so not to rely on fossil fuel based electrical energy. So they prefer to go for something which is more something which is more green, so biodiesel. And then they also have this constant uh, reliable supply of biodiesel, so the supply chain process is quite good. And also they had this challenges initially when they started setting up to get enough contract demand from at the commissioning stage from the utility company. So yes, makes sense. But 9 to 10 years down the line, they still have been maintaining the same setup, even though they have got all the approvals and from the utility companies, the contract demand was increased and all. When we went to do the study, we found that it was barely loading about 40 to 50% of the capacities operation. So when we actually measured and evaluated and compared it's not just about the energy but also the economics. We have seen that it is much more cheaper for them to operate two 250 TR compressor based water cooled chillers rather than operating diesel fired based VAM machines. So because of course, as we have talked about, it's about the efficiencies also. The vapor compression machines are quite efficient in terms of energy conversion compared to the VAM machines. Also, I have also mentioned, if you would have given notice to, never use VAM machines when you do not have any waste heat sources available there. So here the fundamental flaw was they were burning a fuel to generate heat and then using it for VAM machines. So it's like when we after this measures that were implemented, they were able to achieve about 0.27 million dollars worth per annum worth fuel and power savings. And the other thing is, if the facility really wanted to go green, so we have recommended to opt for renewable energy certificates or have some PPA agreements with renewable energy suppliers or install solar panels. Technology upgradation for air handling units. Yes, most of you will be have seen air handling units either in malls or large office spaces and all. So basically, these type of AHUs often have this fans which are either plugged or pulley type driven motors. They may or may not have variable frequency drives in place. And even if they have, the frequencies would either be set in auto or manual mode operations. And it's completely based on the user side pressure requirements. So we have come across this latest technology. It's not latest actually. It's been there around for about at least 4 to 5 years now. The technology is nothing but a DC-based brushless electronically commutated motor driven fans. These are actually much more better in terms of performance. They give higher efficiency and they're compact and reliable. So if you see into the picture on the left, this is a complete setup of CFD panel. You have a motor and then a blower or a fan for the AHU system. And if you see the EC motors, there's hardly this. That's it. It's compact and everything is more efficient. It's even more silent. There's hardly any noise that comes out. So there are a lot of it's quite a niche technology, I would say, patented also. So it's probably a bit more expensive than the conventional ones. So not many are opting for, but I would definitely recommend people to give a try to see how it works. To motivate you all, I would say just look into the numbers here. This is of one of the facility. They were about 10 AHUs, sorry, 12 AHUs. Uh, this is actually a before and after implementation results. If you see, the motor rating has come down. The flow more or less remains the same, the airflow. So the performance, the deliverables are not compromised, and rather you have this improved and the power consumption to deliver the same flow is reduced, almost like say from 36% to 60% in certain cases. So this is something you may also look into for the ventilation systems. Only thing you need to consider here is the availability of this technology for wider range of static pressure requirements. This is again a simple example. For large building facilities, generally for industries or building facility, where the volumes of chilled water quantity is huge, because they have to cater to larger areas to avoid pressure and flow imbalances. They to maintain system stability. Often they have these buffer tanks, which actually takes care of this. Let's say the sudden increase or decrease in the cooling water flow demands. So the sudden fluctuations impact can be avoided on the equipment. Something similar to your the stabilizers in the electrical systems. Any sudden change in voltage fluctuations, it tries to protect your main appliance, right? So we found in one facility that they had two such tanks. You have two tanks. Unfortunately, one was completely properly insulated and the other one was not. More of let's say it's probably some delayed maintenance schedule or negligence. Uh, so the simple principle was just insulate this tank. After the insulation, they have noticed that almost close to $27,000 per annum has been energy cost savings have been achieved on this regard. Case 8, it's about air loss through standby blowers. It's not just for blowers. You can also apply this for fans, different A sections actually. So basically, there was this high capacity blowers for fresh air intake in a large commercial complex building. This air would be actually further passed to filters and then introduced into the indoor air requirements for space conditioning. If you see, generally you have two system where you have this one is always in operation and one is on standby mode. So that way here you have two blowers. One was operating and the other one was standby. When we actually measured the air flows and pressure requirements, I don't have to complicate things with flows and pressure, but just look at the cloth here, which is trying to get sucked into the blower inlet. That means the blower was operating. It was sucking in air and trying to release it into the conditioned space areas. Since there is another blower which is on standby mode connected parallel to this, and both share the same duct, what happens is a part of air is being circulated back to the non-operating blower and it is pushed out. So this way, a certain portion of air that is being for which the fan is the blower is working, it's waste because most of the air is actually coming back within the same place. So yeah, if you look into the cloth here, it is getting blown away. So the only fundamental problem here was they forgot to close a damper when for the non-operational blowers. So this way you are losing air, which means your operating fan is actually working slightly more to give the delivered required air to the user side. So yes, the simple operation was to close or minimize the opening of this damper here, and they were able to simply save about 0.2 lakh units per annum. Boiler performance improvements. Yes. So there was this again a hotel. I would say a 5-star hotel. It had a three tons per hour design and with 10.35 kg per centimeter square design pressure for a diesel fired boiler. We measured its operational efficiency was hardly about 81.8%. This was done through indirect method, so you will have different components of losses also calculated through indirect methods. So we have identified that about almost 10.6% of the heat loss was through flue gas losses. Uh, so for the investigation, we have identified that the tubes, boiler tubes, the heat exchange tubes, were having soot built upon the surface. So due to this, there was poor heat transfer happening, and then since the entire heat could not be absorbed to generate hot water, the heat was being lost with the flue gas. So it was a simple measure. What we have asked them to do is first clean the tubes, and in order to take care of this maintenance, regularly keep monitoring the stack temperature. If the temperature is going beyond certain point, then it is time that they have to clean the tubes rather than waiting for a quarterly schedule of maintenance and operation maintenance measures. So it's better to take a dynamic approach than a passive approach of maintaining a scheduled timeline. This way, they were able to actually save about 26 kiloliters of annual diesel consumption. Last case, use of heat pumps. So this is another hotel, mostly slightly in warmer climatic conditions actually. So they were also using diesel-fired boilers to generate hot water requirements. The city's location and weather conditions were quite suitable for heat pump installation. So why not? We have recommended to install a heat pump integrated with the existing boiler. And of course, the high diesel costs were also actually supporting the change. And by installation of the heat pumps, integrating into the existing boiler conditions to generate your required hot water requirements to the hotel usage, they were able to save about 13.5 kl annual diesel savings. So yes, it's a vast subject. Even a full day session may not be justified, but I wanted to give a flavor of what HVAC system contains and what are the different possible measures that can be put into. I hope I've covered some relevant information for the topics possible in the stipulated time. Presentations do contain a lot of refined information for your reference, so please do go through that once you receive them. In case of any further discussions and queries on the subject, do write to me. I will revert back with detailed explanations or direct you to the useful information. So yeah, every time you engage yourself in with these systems, it can be procuring, operating, or even using these systems. You will be hopefully taking an informed, energy efficient decision now. Thank you.
Thanks for this very interesting presentation, and many thanks C2E2 now for the space to give our presentation today and to participate in this training. So before we dive in the proper presentation on energy efficient transformers, I would like just to give a quick introduction of the United for Efficiency initiative. So U4E, United for Efficiency, it's a global initiative led by UN Environment, funded by the Global Environment Facility, and supported by a wide range of leading global companies and organizations. We provide tailored technical support to countries to transform their markets to more energy efficient lighting, appliances, and equipment to achieve substantial energy, financial, and CO2 savings. So we mainly focus on the 5 products that you see here below: lighting, refrigerators, room air conditioners, motors, and transformers, which together consume almost half of the electricity worldwide. So how do we work? U4E fulfills its mission
through what we call the integrated policy approach, which encompasses the 5 areas or topics that you see here on the screen. Standards and regulation, better known as the minimum energy performance standards, support and policies, which include labeling and communication outreach, monitoring, verification, and enforcement, financial mechanisms, and environmental zone management. So I think this graph might be more clear to picture how all these topics relate with each other. Starting with the development or update of the maps, which is actually the cornerstone from all our projects, and it's based on the market assessment, meaning the market characteristics from each country. These regulations ban those products that are inefficient or obsolete, so we take them out of the capital of the market. Afterwards, we propose a labeling scheme. So we promote energy efficiency products, and we also provide information for end users. And of course, these products usually are the most pricey, and therefore we develop different financial mechanisms and financial incentives along with the banks, local financial institutions. So we bridge this gap, this price gap, and we make products more affordable. At the same time, it doesn't make sense to have MEPs if there's not going to be an MVE system, a monitoring, verification and enforcement system in place that oversees the market and ensures that those MEPs that we previously developed comply. So this includes working with laboratories, testing facilities, on testing standards, methodologies, with the customs, with tools and resources like tracking tools, product registration systems, and so on and so forth. Last but not least, we have the environmental zone management, that it's the proper recollection and final disposal of all products that we are taking out of the market. So that maybe these contain dangerous materials like mercury, refrigerant gas, and so on, and needs a proper treatment. So following all these steps, we ensure a real market transformation, a robust market transformation that's going to be sustainable over time. So we work with a wide range of partners from the industrial sector, like big manufacturers, Osram, Arcelor, Electrolux, also technical organizations like C2E2, the Cooper Association, and of course government institutions, SACRI, the African Energy Commission, etc. And of course the funders and financing agencies that provide the funds to develop the projects, the JEF, Kigali, Green Climate Fund, etc. So U4E currently is present in more than 30 countries with both regional and country projects. On the national side, we provide national strategies, technical support, trainings to policymakers and practitioners. We develop proposals of projects, and we provide support on the fundraising to develop those projects. Onto the regional side, we develop regional market assessments, deliver capacity buildings, and also work on harmonization activities. Now, on the global side, we have a wide range of tools and resources which are available for all countries and policymakers. We have policy guides, the model regulation guidelines that you will listen more in a second, product specification guidelines and manuals, and country saving assessments, which are available for more than 155 countries. So if we have a look at the country saving assessment from Mozambique, the country saving potential is almost 800 gigawatt hour. And we can reduce this electricity, which will worth $95 million US annual in 2030 and represents almost 1 million tons of CO2. Sorry. If we apply MEPS today, transformers share 7% of the savings I have just said. So having a closer look at the transformers, we can see in this chart that if no policies are implemented by 2030, the electricity consumption used by transformers would increase over 35%. If we implement MEPS, this increase would be reduced by 8%, and it can be reduced another 8% if those MEPS are more stringent, more ambitious. So as you can see here, we can achieve just with the switch to more energy efficient transformers, we can achieve savings of 55 gigawatts hour, 35,000 tons of CO2, and achieve more than $3 million savings on the electricity bill. So this is basically all from my side. With this positive scenario, I will leave the floor to my colleague Mayur so he can explain more in detail how to make the most of the savings locked in the transformers. Thank you so much.
Myself, Mayur Karmarkar. We are working together with UN Environment for the United for Efficiency program. And we chose distribution transformer as the product example, which is very important for the utility business. And with this product example, you can see the content of the program, as well as takeaway would be the policy documents and the specification which was created in the program, which can be used by the utility on an immediate basis. So first, when we talk about the distribution transformer under United for Efficiency program, the program has developed various tools, as Sol mentioned. So first one is the model regulation guideline for energy performance requirement for distribution transformer. This is a guidance book to assist governments and the utilities in the developing and emerging economies that are considering to regulate or create the legislative framework for the distribution transformer efficiency performance standard. This document can be downloaded from the U4E website, and the link is provided here in the presentation. So the document will look like this, and the document will contain the details as Sol mentioned, in terms of all the attributes related to the environment friendly and energy efficiency performance management of transformer. As you all from the transformer industry, I know in Mozambique you got the voltages right from 400 kV, which is the highest transmission voltage in Mozambique, which is connecting with the neighboring countries with that high voltage. So the utility assets are, starting from the 400 kV up to the lowest voltage is 6.6 kV in some of the areas, the distribution voltage, and then the voltage at the user end is 440 volts like IEC standard. So you can see in the transformer, in spite of being the static device, and is one of the efficient electrical product, because this product is in the chain from 400 kV volts up to sub-distribution level and distribution level. There are various voltage transformations are happening, and cumulatively these transformers are adding losses to the tune of 5 to 6% as the technical losses. In some cases, it will be even higher, and therefore this transformer becomes a very important product to regulate. Another important thing from the utility perspective is that this is, this is a product where the technical losses are higher, and there is the potential to reduce those losses. These transformers, as you all know, works for 24/7, and the life of this transformer is 25 years or even more. So having the energy efficient transformer is going to create a sustainable impact to the environment and also to the utility economics on a long-term basis. The electrification rate in Mozambique is one of the highest rate there in African continent. The generation capacities are being added, and there have been long-term planning has been done to add generation capacities. As a result of that, this inventory of this transformer you have today is likely to double in less than 10 years' time if all programs goes well. So this product, from the utility perspective, you being the national utility, reaching all the corner, you can take one step forward in regulating this transformer market on behalf of the government and be the torch bearer for the energy efficiency program. Going forward, when we talk about the transformer policy guidebook, it contains the two most common type of transformer, which is liquid filled transformer, which has generally two windings for stepping up or stepping down, and these are insulated with liquid, which is normally the mineral oil, but nowadays with the esters coming in, this is alternative and sometimes natural ester preferred as a green recyclable material. So the first category is a liquid fit transformer, which is covered in the guidebook. And then these transformers can be used for generation, particularly at these new solars and the wind power plants which are coming in. And this transformer also can be, supplying the electricity to the customers, such as residential customer, commercial customer, industrial customer, etc. So the guidebook also, policy guidebook also includes the dry type transformer. These dry type transformers are generally air-cooled transformers installed in the densely populated buildings, mainly providing the issues related, addressing the issues related to leakages, and then the other issues such as fire, etc. So this document also includes these two types of transformer commonly used in the distribution network. As you know that these transformers are, the efficiency can be addressed in two ways here. The one way, currently the efficiency, as you know, this distribution transformer has two components of losses. One is the no load loss, which is the constant loss running in where the energy is consumed and the heat is generated by 24/7. And second one is the copper loss or the winding losses, which are load losses, which are directly proportional to the square of the load. So these transformer will have these two components of the losses, and as the loading increases, the importance of load loss becomes very vital. And having the transformer with lower load losses is going to run the transformer cooler, trying to make it more compact, etc. So particularly for the urban power infrastructure, the need is having the compact transformer which generates lesser heat so that you don't have a big cooling system needed for this transformer. And if you plot the efficiency curve, you can find that the efficiency is generally at the maximum at 40 to 50% of the load, sometimes even at the lower load percentage. And there are the technical solutions available in order to improve the efficiency performance with the different material with different design options. And there are the new generation of the materials which can reduce the no load losses even further. There are the ways and means which OEMs knows to comply the regulation requirement without investing into additional manufacturing infrastructure, but just by changing the design. So while leapfrogging of the transformer energy efficiency is needed, although these transformers generally are procured on a life cycle cost basis by the utility. In most of the cases, there is a opportunity to improve the performance over the MEPS. Like you have seen in an earlier presentation that the MEPS sets the bare minimum, but the labels encourages the higher efficiency market. The same thing if the MEPS establishes the minimum baseline for the procurement or the energy consumption in transformer. The life cycle cost-based purchase adds the further energy efficiency and gives you a right solution for your system. This ultimately the saving of the energy is translating into a peak load saving, lower electricity bill as a distributor, as a distribution company, and also greater reliability of the supply on a longer term. A payback period of these transformers varies from cost of purchase, etc., and the generation mix. But assuming that the current average cost of purchase of 6 cents a dollar, the payback period for energy efficient transformers can be less than 6 to 7 years. So this is a very attractive proposition because for the utility for a product which is having a life longer than 30 years. And the saving potential, particularly it exists 400 terawatt hours or 220 million tons of CO2 emission by 2030 for the countries where there is no regulation. So that you can see that countries in a red are lacking the national mandatory efficiency policies, and most of the African continent includes them. So there, therefore, this opportunity is a low-hanging fruit for Mozambique, because today we are talking to the utility who owns more than 90% of the transformers assets in the country. So the examples of MEPS in a different country. So this slide basically is trying to translate the various comparison or the minimum standards and the aspirations of Europe in Tier 2, which is 2021, which is happening in the next year. So the countries which have developed the MEPS standard, they have generally into two types. Mostly the European countries have developed the MEPS in terms of load loss and no load loss. That are the minimum requirements. So those are maximum losses allowable in the country. Whereas the US country is trying to regulate the market by the efficiency at 50%. So for making the simplification of this complex way of measuring performance, we have converted all the countries' regulation at the 50% level for the comparison purpose. You can see here from the the European Tier 2 would be the best possible example starting from 2021. So this would be the efficiency standard almost reaching towards the 100% for the higher sizes of transformer. The most important thing you also have to note here is that the efficiency performance of transformer improves as the size increases, because of the smaller size equipment cannot be made as efficient as the larger size equipment due to geometric reasons. You can find that the efficiency curve with respect to different kVA rating are is not the same, which ideally should have been. The example of MEPS, particularly for this dry-type transformer, program are written here, which is for the different country, different programs which are happening, and what is the energy level map. So the ambition for the country in Africa, wherein the most of the purchases currently are happening, new electrification, and Africa would be the tomorrow's largest market for the electricity. I think the aspirations and the ambitions for Africa to match the best available in the world, it cannot be underestimated. So this is where the aspiration of the utilities, particularly for the where the electrification is a major investment likely to happen. The policy guidebook further also provides the recommendation on the product standards, which are generally in line with IEC 60076. This policy guidebook also covers the recommendation for the countries adopting 60 Hz standard and 50 Hz standard as IEC. 60 Hz standards are generally followed in North America and Americas and smaller markets like Philippines in Asia. The guidebook also provides the supporting policies related to the labels. The labels are quite useful tool for the transformers if they are purchased largely for the buildings, and this is what where you have larger commercial and industrial transformer customer market. So that is where the label as a supporting policy will be helpful. Then the communication campaign of energy efficient transformer, largely led by the utility, will create the longer impact on other markets. The other important supporting policies, particularly for the country where the T&D losses, the technical losses and commercial losses are very high, is about how the incentive scheme can be created by the regulator and the government through a tariff mechanism. So that is the another supporting policy which is very prominent for the country like Mozambique. The policy guidebook also recommends the monitoring, verification, and enforcement policy, the best practices followed in the other countries. It provides the information related to the financial mechanism. The financial mechanism, particularly for these type of the products, where the finance sometimes comes from the multilateral development agencies, such as African Development Bank, World Bank, and then EU funds, etc. So these multilateral and the bilateral funding financial option, this financial mechanism will be helpful to transfer the market and transform the market to the energy efficient transformer. This policy guidebook also includes an important aspect of environmental management. And here I want to take a little time. The transformer oil, which was processed 20 or 30 years ago, they used to add certain chemicals which contain the polychlorinated biophenyl, which is popularly known as PCBs. Those are toxic elements and which is classified under persistent organic pollutant. So these there are various government programs and also the UN environment program in order to claim or reclaim these PCBs from the environment and dispose it in a most environmental sounded way, because this PCB's contamination is going to pollute the groundwater, soil, and so many other environmental components. Now, these PCB has a good insulation properties and stabilizing properties. Therefore, this material was used in transformer oil produced 2 or 3 decades ago. So as a result of that, most of the old transformer oils, which are this PCB element, has to be replaced with the new one. And there are the special grants and the funds are available internationally through UN organization for managing that inventory of PCB and disposing the old PCB stocks, even for the utility. So these guidebooks provide the information about the Stockholm Convention of these pollutants and provides the information and help for the recipient for managing those PCB, and also promote the new materials which are recyclable, such as the natural ester liquid, which is very good for the thermal properties and also recyclability. So, particularly in Africa, the Southern African utility like ESCOM, they have strategically decided to use these natural esters, which is to make the transformer environmentally sustainable, 100% recyclable, and also this liquid is helping utilities to make the manage the loads more sustainable way, so that the transformers can handle more capacities for the short term duration or the peak load condition. So this is something which is very important, particularly for the EDM when they are looking at the environmental management as a utility business. The United for Efficiency program has also created the ready technical specification. We have, when we had the stakeholders meeting and the meeting with particularly from representation of the South African Power Pool and then other African agencies, we realized that utility wants the help in terms of creating the procurement specification which they can adopt, and therefore the project has created the procurement guideline or procurement specification for these efficient and also the environmentally managed transformers. So the salient feature, these specifications are also available as a resource material, and I will encourage you to download that and use it for your procurement. This document can be also used by the individual industries and the commercial customer for the procurement. The salient features of this document is that this can be used by any utility or any customer and also the government. This document provides the the two level of fire safety information. One is the normal fire safe transformer, and other one is increased fire safe transformer. Increased fire safety also comes out of the ester, which has a higher boiling point of 300 degree and above. As a result of that, this liquid has getting more popularity over the mineral oil, which is the crude oil derivative. The specification also provides a balance between this general and the specific requirement. You as the utility, maintaining a balance between the general and the specific requirement of any purchases is very crucial. So this ready reckoner helps to provide that balance. So this document is necessarily into one main part and two annexes. The one is a general guideline which provides all the information related technical specification of a transformer, but the two annexes provides the specific information such as the impedance requirement and then the voltage level and the tapping range, etc., for the 50 hertz and the 60 hertz market. There is Annexure B and Annexure C. Also, this document can be adopted easily and can use the baseline document and can make a unique specification by adding additional feature to the annexure. This is a very flexible, user-friendly document. So the sample technical specification provides the necessary comments for illustrating the need of each clause, and it is annexed with the specific technical requirement for against that particular clause. It also provides the flexibility of including your values such as voltage level, then the highest system voltage level, then the basic insulation level, etc. by in a spaces provided in the gray, so that you can just enter this value here and then use this document for your purchases. This document promotes the life cycle cost-based purchase, where the MAPS, the minimum energy performance standard, as per the policy guidebook, which I shared earlier, is the minimum thing, and then the life cycle cost-based approach, the total owning cost, help for evaluation of the bids from the different bidder. Uh, the next and very important thing for the utility business is that the transformer is a thing which it's very expensive to replace the transformer for the energy efficiency. It does not like a light fitting where you replace the incandescent lamp with the LED at a lower, cheaper cost. So the cost of replacement of the transformer is very high. Mostly utility has to get such cost approved to a regulator, and the regulator wants to have the justification, and overall it increases the capex requirement of replacing this transformer. Particularly the replacement of the transformer is expensive on the return over investment basis, where the ROI for such type of the projects is very high, can be somewhere around, the percentage is, in terms of the number, simple payback period, it can be more than 8-10 years or even more in some cases, depending on the load factor of the system. So what the Indian utilities have started doing now is that instead of buying a new transformer where there are a lot of hassle to convince the regulator, justify the ROI, etc., they are trying to improve the performance of the existing inventory through active repair. And I will be very happy to share that case study with you. Generally, the old legacy transformer improvement KPI can be for the loss reduction, that is the total technical loss reduction, which is no load loss and load loss. Then the reliability improvement by making transformer hotspot temperature lower or reducing the DC failure, DT failure rates by including the protection devices, etc. And then the third one is the KVA capacity enhancement. That is where you make the transformer suitable for frequent overloading in order to address the overloading issues. Now let's see why what is the driver for the Indian utility to select those KPIs. So the driver here are naturally the failure rate and the huge spend on renovation and modernization and replacement of the DTs. India, the installed stock of these transformers, distribution transformer in the national utility or the state utility sector is around 12.5 million units, which is a huge number. In terms of the capacity, it is around 220,000 MVA. The DT failure rate in India is higher mainly after 100% electrification has been done because of the overloading which is happening because of the theft and the faulty, mostly it is overloading is happening because of the intermittent loads coming through the theft and unmetered connection. So as a result of that, also the poor asset management is one of the important reasons. So as a result of that, the failure rate is 10 to 12%. And the definition of the failure here is that any transformer which is there is a deviation with respect to the performance which is there in the utility specification, that the product which is deviating to that in a working condition is called as the failure. Which may include the oil leakage, which may include bushing damage, and many other things. So the cost of this repair and maintenance of this transformer is around 30 billion Mozambique currency. For a change, the Mozambique is the country where the exchange rate of Mozambique currency with the Indian currency is 1:1. So as a result of that, 3,000 crore, which is method of Indian counting, is directly equal to 30 billion of the Mozambique local currency. So this currency is this is the economic impact to the utility overall, which is generally directly passed on to the consumer, and it is being paid in form of the electricity tariff by the consumer. So that's the saving potential for the consumer. So the average technical losses on this transformer is around 3%. So energy efficiency is very important. And then the AT&C losses in India are 24%. Now these AT&C losses in India 24%, which is higher than Mozambique. I think Mozambique is somewhere around 20%, but still the technical losses will be similar. So the trend is to sweat out the existing assets rather than buying new ones. So as a result of that, we actually have created the intervention, and then the utility has adopted the revised practices of the rewinding and repair, etc., where the KPI has been set for the performance improvement. For example, improving the KVA capacity or reducing the losses or improving the reliability, etc. So the business change is that the utility has started doing the detailed inspection of the transformer which comes for the repair, and then accordingly take the decision, and then the repair unit will follow the same processes after the initial inspection and testing, wherein both load loss, and then the calibration of the temperature rise will be done through a software. And then after the transformer is repaired, the same transformer's new performance is measured as per the IEC standard, and then the improvement for this transformer will be rewarded to the repairer through a performance-based contract term. So the actual result, actual case, I just want to share for your benefit that the 100 kVA transformer, I think the rating is also very similar to Mozambique here. So 100 kVA transformer, where the medium voltage is 11 kV, the secondary voltage is 433 volt. It's a delta star transformer. The KVA capacity of this transformer when it was assessed through the software was 86 kVA. And we realized that reduction of the KVA capacity is mainly due to the insufficient cooling, and also while doing the previous repairs on the transformer, this transformer was repaired 2 times earlier. We have seen that some of the less material was put back in the transformer. As a result of that, the KVA capacity was lost. Now the utility specification provides it for the 100 kVA, but they were actually using 86 kVA. As a result of that, this transformer was failed 2 times because of the overloading. And then this transformer also had the losses higher to the tune of 34% compared to the specification. So after redesigning of this transformer at the time of repair, the KVA capacity was enhanced by 20% and the losses were reduced by the 50%. So the economic payback period for these transformers was seen as 1.66 year just by redesigning at the time of repair. The losses were reduced considerably. Also the energy saving was achieved, and that through the energy saving, the payback period was only 1.66 year with average cost of 6 MZN, cost of energy. In India, the cost of electricity is a bit higher, perhaps compared to Mozambique, is mainly because of the generation mix and also the duty which is paid by the generator for the coal power which they are purchasing. So as a result of that, these utilities buying power, and also the peak power which they buy during the peak time is more expensive. So levelized average cost of electricity is around 6.25 MZN compared to the maybe higher than the Mozambique. But therefore, the payback period with the normal repair cost is 11,000 Mozambique dollar or Mozambique currency. And then the incremental cost due to active repair was 86,000, but the payback period was only 1.66 year. The same thing if you consider the salvage value of the newly added materials such as copper or the steel, etc., your payback period be in just few months. Now, if you have to convert that into a business model, let's see how these can be implemented at the utility level. So there should be some funds which would be available in Mozambique, which would be the energy efficiency funds, which can be accessed clearly by the utility, or sometimes World Bank or African Development Bank has those funds. Those funds can be used for such active repair, where the ROI is very high, so that you can pay back this money with the help of shared saving and improve reliability, avoided the purchase cost, etc. Pay back those incremental costs or the funds back to the development bank, and this is a very profitable situation. Now, while taking this such type of the program, the issue needs to be addressed is the standardization of the active repair solution. So a few technical experts along with the repairer can sit and standardize this solution. Then the skill set of the repairer, the human resource skill set, so there has to be some training for them. Then there also has to be expertise in a material procurement required for repair. If you are outsourcing this repair through the vendors, then your vendor evaluation, vendor selection is the process which needs to be addressed. You have to make sure that the testing capability accredited are available with the utility in order to establish the baseline and also see the improvement. And if the local vendors don't have the designs with them, you may need to look at the design support they have or they qualify with for such type of the work. I think these type of the efficiency improvement programs can be implemented without any additional regulation needed or without any intervention of any other agency. And this such type of the program, if it is piloted by Mozambique within Africa, I think the other African country can quickly learn and it can be transferred to Eastern African countries as well as the other Southern African countries. With that, I would like to close my presentation. I think we are overrun by time, total 30 minutes, which of the total allocated time. So sorry for that. And we'll be happy to have any questions from you. Thank you.
Thank you so much, all the panelists, for the very interesting presentations. Now I would like to introduce the Q&A session. And we have received questions for Rahul that I would like to introduce now. So Rahul, as you can see in the screen, the two questions are as follows, and I will introduce them at once. The first question: how can the design of buildings and systems help to reduce their heating and cooling needs? And the second question: how do I know that my system has a correct size power for the compartment, considering not only the size of the room or system, but also the temperature of the place, the seasons, etc.?
Thank you, Begonia. So, firstly, I think I'll try to, the answer might overlap for both these questions. So, I'll be answering for both the questions. Firstly, if possible, since we are talking about designing of systems and buildings, I would rather design my buildings first based on my purpose and usage, not talking about the aesthetics here. And then that is, if I have to keep myself warm in a colder region, then that is that is a requirement. Or if the design is something, if I have to keep myself comfortable in a warm or dry or humid climate, then that is a design requirement. So yes, I would design as per my requirements the building, and then I would design my systems as per the heating and cooling needs. So we are talking about needs here. When you say you need a certain cooling or heating level, you should be able to provide them, not to reduce them. For saving energy or something, I would not recommend to compromise on occupant comforts in the first place. So from here, I think the Q2, the question 2 also slightly overlaps here from the first one. If I understand what the participant is actually intending to ask, see, basically the building design primarily is based on your individual choices. Some may want it efficient, some may focus on aesthetics. So I would recommend you to look into the presentation of building envelope that was delivered earlier this week. It should give a good picture on the factors that you may have to focus on the envelope part. That is, it depends on your climatic zones, the type of materials, that is walls, floors, roofs, the insulations, the windows and glazings, the type of technical parameters like U values and R values, the better insulation and all. So more details are actually available in the building envelope presentation. It should cater to all your design questions on how design of the building can reduce the cooling or heating loads, if something that is what it is intended to ask. When it comes to active systems, you can know if you have correct size or correct power consumption. Basically, let's say in case of power, you can measure through the power analyzers, or you should be able to see that value on your digital electrical panels and all for that particular component. So compare it with your rated design power. If the operating power is close to the design values, then the system sizes and all are quite acceptable. If it is way too high, then that means you are overloading the system. That at times that means your systems are actually designed for a lower capacity and you are actually overusing it. If it is way too low, that means you have over designed your systems that are installed because they are operating in part load conditions and all. So that is one of the methods you can look into it. Then the size of HVAC systems can also be looked into it through measurements of heating and cooling loads. It could be for your air conditioning units or chillers. It can, if it is for your specific compartment or a room, then I'm sure you will be having a dedicated, possible dedicated air conditioning unit there or heating unit there, so that measurements can be done as I've shown in the slides. Or it can also be through the airflow or water flow measurements if you're talking about in case of fans and pumps, blowers and all. It is important that you have the rated design values in place and compare your measured or identified parameters. For cooling and heating loads, if you cannot measure, then you can also theoretically calculate to estimate, on what your actual system capacities could be. You may have to take several factors into account though. That is like the solar radiation levels, your ambient conditions, the wet bulb, dry bulb temperature, humidity, the orientation of the building, how is it facing, is it east, west, north, south, the occupancy rates, how many people are staying in that particular compartment, room or a building, infiltration or leakage rates if there are any. Technical data, the R values or U values of the windows, walls, roofs, glazing details. The idea of efficiencies, or you should also be having an idea of efficiencies of the cooling or the heating system that you intend to procure, if in case you are talking about design. Then based on all these parameters, you can actually theoretically calculate and see what is your heating or cooling requirements, and then compare with the existing systems. Is it something what you have calculated? Is it matching, or is it like over capacities are available, or these systems are actually under design based on your theoretical loads? So yes, more details. I think you can actually refer to ASHRAE standards also, because they do have this in-depth literature and standards available with them with respect to these factors on designing factors. It's not just about you do have these standards on conversion factors, like based on your area or based on the number of people that you occupy, occupancy levels and all. You can they have these conversion factors of identifying the approximate cooling load that is required, or they also have these methodology on how to evaluate theoretically based on these factors, to calculate and see how the cooling load or heating load can be reduced. Reducing or optimizing of your heat loads need not necessarily also be something more extreme enough to change your existing, so that you have to change your designs of your buildings and systems in place. They could be as simple as segregating your heating and cooling loads. Like I have seen in many modern offices buildings, where they have these coffee machines and water coolers, all are placed in the conditioned area. Such kind of appliances also do add to your cooling load, because they do ultimately the electricity energy consumed will have to be dissipated in form of heat in the cooling area, right? Conditioned area. So if you can actually move these appliances to a non-conditioned area, then you could probably look into possibilities of reducing the cooling loads. Some simple measures like your outdoor outdoor units, you can keep it in a shaded area, because if you look into the air conditioning units, you have an indoor unit and an outdoor unit, the condenser unit. If in case it matters a lot if you are able to place them in a shaded area, because you cannot just expect heat is efficiently released out of that condenser unit or outdoor unit if you place them in an open, already hot and sunny area, right? So that way you can actually reduce optimize your sizes and equipment. You can also take actually support of technological support, I would say, but again, this is not directly related to heating and cooling, but to an extent, yes, your energy power consumption. For example, I think I have seen some softwares coming up in the market now, which can be installed into your computer systems, which actually reduces the computing power, uh, optimizes and reduces the computing power. So imagine you have office spaces of hundreds of computers, which are not continuously operational, but they are mostly on standby mode or simply switched on and not working and all. So that way, this kind of optimization can happen in cutting down the power consumption. So yes, while you can take several step-by-step approaches on optimizing your consumption, it is or reducing or optimizing your cooling or heating loads, or take any design decisions. It is always advisable, to take a professional support when you are doing these activities. Thank you.
Thank you so much, Rahul, for the explanation. We haven't received any question for Mayur or Soledad, so I encourage you, if you still will have questions, to contact them through their email or also contact Rahul. So now, well, ladies and gentlemen, finally we come to the end of the training session. I would like to say thank you to the panelists for the informative and interesting presentations, and to the audience for their active participation. We hope that the presentations will be beneficial for all the stakeholders involved in energy efficiency. Thank you so much for your attention, and wish you a good day or night from Copenhagen.